technical session on hands-on modeling for electric vehicle signal processing based model. In this session, we have an expert from industry and she is respected Ira Bajpayee ma'am. She did her BTech in 2018 in Electrical and Electronics Engineering from Institute of Technology, Kanpur. Then she did her MTech in 2022 in the field of renewable energy from Rajiv Gandhi Institute of Petroleum Technology, Bangalore. And her areas of interest are electric vehicle, battery management system, smart grids, and related domains. She is certified specialist in hardware and loop. And at present, she is application engineer at Quadzi Infotech, which is a franchisee of Typhoon Hill. I now invite Ira Bajpayee ma'am to take over the session.
Thank you, Soumya, for the introduction. Hi, everyone. Good evening. So let's begin the session where we left off in the last session. So as we started doing a hands-on model on electric vehicle-based signal processing model, so we initially, developed around 2 subsystems out of the total 5 subsystem block that were supposed to be developed. So we will continue building the same model. As you can see in my screen, I have opened the same model which we created last time. So hope you all are also ready with your software. If not, I'm just giving you 1 minute time so you all can open the same example model in your PCs, and then let's start with the third subsystem, that is mechanical transmission unit. Before that, just let me know if my screen is visible and I'm properly audible. Can somebody confirm?
Yes, ma'am. The screen is visual and you are audible.
Thank you. So I'm waiting for a few seconds and then let's start. Meanwhile, you all can open the model.
Good evening, Ira.
Yes, sir. Good evening,
Actually,
sir.
before this talk, I had talk. So that is
Yes,
why
sir.
I was not available during when you were introduced. I'm very sorry for that. I welcome to you.
Okay, sir.
I hope
Okay.
my learners already welcome you.
Yes, sir. Yes, sir. The introduction was given. And
Thank you.
thank you, sir. Okay, sir. Okay, then let's start with the third subsystem. So until now, we have created 2 subsystem block. The first one is lithium ion battery pack, and the second one is the electric drive unit. So we know that in the vehicle that we are creating, we are using it based on, developing the model or based on the components of the signal processing library. And this complete library is, having certain blocks which are defined in blue color. And as I specified initially during the session, that Typhoon is basically having 2 different type of processors. One is for running the plant side simulation at a lower rate, that is for a nanosecond scale, and the second one is for a CPU side simulation, in which we run the signal processing and the controller side part at the microsecond level. So now we have the third unit, which is the mechanical transmission. So as we know that in this subsystem, all the subsystems are actually connected to each other, and there will be some or the other signal which will be interacting with the other units as well. So let's see what is there inside the mechanical transmission. So just like we did last time, double click on the mechanical transmission subsystem block. We will just delete the part which is already mentioned there, and we'll start developing the model. So let's first take a component called signal input port, and next we will take another signal input port, and lastly we will take a signal output port. Next, let's just type in and take a termination block. So we are using this termination to denote what type of, movement will happen when we apply the brake force. So definitely termination means ending something. So we will just give this particular signal towards termination. So the name of this signal, I will keep it as brake force. Next, we have the termination block. Then at the bottom, we will be taking another subsystem here. So just search for a subsystem block and we can just place it like that. And beside it, we are going to take a gain block. After the gain, we will take a signal output port. Similarly, at the bottom, we will take another gain block. We are going to reverse the direction, connect the output to the next output, and we will take over here a signal input port. I'm also going to place it in such a way that I will flip it and connect the output of this signal input to the gain block. So I hope till this part it is clear. Now we will also name other input outputs. So we have DC motor torque, and the next one we have is DC motor speed. The gain blocks that we have taken, they are representing the mechanical transmission ratio. So we are going to name them as MT ratio. Again, the value of this has been pre-calculated for this example. It is by using the standard equations. So there will be the value for both the blocks, it will remain the same. And lastly, we are just converting these particular, torque and speed signals into the transmission unit signal. So whatever mechanical parameters we had, now they have been transmitted and converted to force and the velocity signal. So we have wheel force and then we have wheel velocity. Next, the name of the subsystem is efficiency. Inside this block, again, we will take a signal input port. After this, we will take another gain block. Another gain block we will take at the bottom. Over here, we will take a component called signal switch. Let me name the gain blocks. So this one will be traction. And this one will be braking. After this, we will take a termination block over here, connected to the output of the switch. And at the top, we will take a signal output port. Now we will connect the braking input also to this, input that is coming from the signal input port. We will connect the top control signal of the switch also to the same line and the output to the control signal. Let me just connect traction and braking to the signal switch. I will explain now what we have created here is we are just trying to see the efficiency of the system. So the input that is coming over here is our DC motor torque. Now torque, as you know, is applied from the machine which is inside the vehicle. When the last session before starting this model, one was the positive force, which we also know as traction force or propulsion force, and there was also the resistive force. So in case of traction force, whenever the motor or the machine is supplying some torque, then only the vehicle becomes in motion, and that is the positive force. And then it is having a factor with the resistive forces, and we get a net force, which is basically the force which is helpful to let us know what type of propulsion is the machine doing. So in this case, whenever the torque input is coming, we are getting the information and we are, just multiplying it with a factor uh, for the traction and the braking gain, and then moving towards the signal switch. In both case, if there is some torque available, definitely the machine will be in motion. So our traction force will be greater, so the signal switch condition will be true, and we will get some output which will be our wheel force. But in case we don't get any input in the torque command, the braking will be automatically considered and the vehicle will be stationary. So that value will automatically go to the termination block. So that is what this particular signal switch condition is denoting. Now let's just name the traction and braking. Just define the value of traction and braking gain. So double click on traction. So this one is 0.92. And for the braking, it is 1 divided by 0.92. Just reverse of the first one. Traction and braking. 0.92 and 1 divided by 0.92. Then I will come back to the mechanical transmission unit. So at the top over here, you can see root, mechanical transmission and efficiency. So from efficiency, we will go back to the mechanical transmission subsystem. Now we have the input and the output. So let's connect it to the row. And everything looks okay. Then we have to define the value of the empty ratio. So double click, the value will be same in both the lines. The value is 15.0654. The second one as well, 15.0654. Okay. Now we have completed the mechanical transmission unit. So I hope all have completed till here. Is anyone still doing it, or we can continue to the next subsystem? Okay, so let's just continue to the next one, which is the vehicle dynamic unit. Let me just check one thing. The signal switch condition. Okay, just one little change in the signal switch. We will select the condition of the switch to pass the signal with the control command greater or equal to the threshold. And the threshold value, we are going to put it as 0. Let's come back to the root window. Now we have the fourth subsystem, that is the vehicle dynamic part. So let's quickly start making the model. We will delete the initial part. Now let's start with the blocks. So again, we will take couple of input output. So let's search for signal input block. After this, we will take a sum unit. We will just change the symbol of the unit. So it will be plus minus. The input we are going to connect at the top of the sum block. After this, we will have a gain block. After the gain, we have the integrator block. And then we have signal output port. So 2 of them we will be taking. Let's place it like that. Next, we will take another block, that is probe over here. So again, to just, kind of visualize the signal that we are planning to use here. Okay. Let's start naming them. So we have wheel force here. After that, we have vehicle tractive force. Vehicle tractive force. Next, we have the gain block by the name of mass. Integrator will be same. The output, we will name it as vehicle velocity. Then we have another gain, another signal output. Again, we will name it as vehicle velocity. At the bottom of this, now we will take a product block. We are going to flip the direction. And instead of 2, we will take 3 multiplication sign. The top part, we are just going to connect it to the same line. The second arrow, again, we are going to take it here. The third one, we are going to connect to a constant block. We can flip this and just connect the constant here. Here we will be taking a termination block and we will connect another constant here. So the output of the product will become the input for the first, input for the sum. The second input will be again connected to another constant block. Again, we can flip and connect it. And the third one, we have again a constant block and a gain block. Here we will take a signal switch. At the top, we will absolute value. I'm just going to rotate it downwards because this is going to go as input to the signal switch. And this absolute value input is going from the velocity, the vehicle velocity signal. At the bottom here, again, I'm taking one constant block and just connect it to the false part of the switch. The true part will be connected to the sum signal, the output of the sum signal. And lastly, over here, we will take signal output port, and along with that, we will also take a probe. Now we can just, one by one name all the components what we have taken. So again, this output at the top you can see is the wheel force or the traction force. Now what we are doing is we are calculating the vehicle resistive force as well, so that we know what is the net force. So now for calculating the vehicle resistive force, let's see what all input we are considering. If you remember, we discussed about some of the equations that are being used. So this is the vehicle resistive estimated. Then at the bottom we have the resistance force. Over here at the gain block, we will name it as mass, and will be the road slope block. In the bracket percentage. Above that, we have the rolling resistive force. At the top of that, we have the aerodynamism coefficient. So if you remember, following the same equations, we have the aerodynamism coefficient. In that equation, we basically use the mass and along with that, the velocity square and the aerodynamism coefficient as well. So all three we have considered. If you remember, mass was usually used in all the equations. So along with that, we have the rolling resistive force. So this is the total force which is calculated. So already it consists of all the calculated value for mass and rolling resistive coefficient and so on. So whatever total value was calculated, we will directly feed it here. And the third one, that is road slope, so this one is for the gradient force. So if you remember, whenever the vehicle is moving up or down the slope, so there will be some angular force applied. However, the value of the slope will be 0 in this example, but at the front of that you can see again the same multiplication with the mass and gravity, and then going towards as an input to the rolling resistance. So this is just demonstrated to explain how the rolling resistive is basically calculated. Over here at the top, you can see there is one signal coming from the constant which is going to termination directly. So this is the wind speed. So in this case they are considering zero wind speed also. So that's why the aerodynamism force in which the wind factor is taken, that will actually not be considered in this example. So again, let's just quickly name all the blocks, and after that we will just provide all the values. Okay, I can see one signal we did not connect, that is the bottom of the sum block. So this is definitely the difference between the traction and the resistive force to calculate the net force. So just connect the minus part of the sum block directly with the resistive force. Now we will just name the constant again. This one is wind speed. This is in MPS or miles per second. And I think all the blocks we have named, that's it. So let's start providing the values. So very first we have the mass block. So just double click and we will provide the value as 1 divided by 692. Next, we have the switch block. Inside the switch block, we have the condition control is greater than threshold, and we will keep the threshold same at 0.5. The vehicle resistive force will be same at 0. So we'll just set the value to 0. After this, we have the wind speed constant. So this value is again 0. Next, we have the aerodynamism coefficient. So usually this is between 0.4 to 5. So it is kept at 0.428 in this example. Next, we have the rolling resistive force. So this is calculated as 135.77. And lastly, the road slope is again 0. And since this one is in percentage, so mass and gravity will be 692 multiplied by 9.81, and this is then divided by 100 to convert the percentage to the factor. 692 is basically the value for the mass of the vehicle. So this is it. We have just provided the inputs for all the blocks. I think so this subsystem is also complete. So is anyone having any questions till this part, or anyone is just completing, or we can move to the next one? Okay, I hope you all are able to follow. Let me just check the chat also. Okay. Let's move back to the vehicle control and the EMS part. Again, double click on the subsystem. Let's start creating the last subsystem part also. So once this subsystem is complete, our entire model will be completed and we can directly move towards the SCADA panel. So let's start taking the blocks. In the vehicle control unit, as you know, this is the essential part of the machine. It is basically controlling, monitoring all the things for all the subsystems. So there will be multiple input output that are connected over here. So very first of all, let's start again with a signal input port. Let's keep naming them also. So this one is coming from the battery part. So the name is battery SOC. After this, we will just take a gain block. So the calculated SOC will be somewhere in a decimal place. So we will just convert that to percentage. So I will just change the name of this gain block to percentage, and we will connect a probe over here to measure the percentage of SOC of the vehicle. So let's name the probe as battery SOC estimated. At the bottom here, we will connect a signal switch, and the control input of the signal switch will be connected directly to the SOC. We will take two constant blocks here. The first one, I will just connect it to the true part. And the second one also, I'll connect it to the false part. The output of the signal switch, I will just connect to a signal output port. Next, just name both the blocks. So this one is, or we can just name both at once. I will just hide the name of this one, just placing it like that. And I will name this as electric braking. And the output is named as brake force. Next, we will take a clock input. Next, we will take a block for the input of the drive cycle. So over here, we are going to take a different block by the name of 1D lookup table. The lookup table is basically used when we want to provide some value, which is basically x, and x is the function of y. So we have, vector input, or I would say multiple data points for x and the function of x, and we will just directly feed them here. So the output will automatically as per the value that we have fed in the x and the fx part of this component. So let's search for the 1D lookup table, and we will just connect it from the clock, and I will just name this as ECE drive cycle, or driving cycle. Let me just put it a little bit lower. Okay. Let's take a gain block at the top. We'll connect the output here, and we will connect a probe to the output of the gain. Let's name it as 2 kmph, and the probe as requested speed. At the bottom, I will take another subsystem block. Below this, again, I will take a gain block. Similarly, another probe over here. Let's connect them. And again, connect this one to the initial input. So we will take a signal input port. Now again, I'll change the name. This one is vehicle velocity. The gain block is known as 2 kmph. Okay, I've used the same syntax. And the probe will be the vehicle speed. So what we are doing is, because this is the controller part, we are just having a subsystem block here, which you see. It's going to do the operation of the PI control. So we know about, very common PID controllers. So usually the PI control is implemented inside such strategies, and it will be doing the proportional as well as the integral based control. So what we have to provide as an input is the reference speed that we want to set, and what is the measured speed that we have from the vehicle. So once we compare the two, whatever error we get, accordingly the controller behavior is shifted, and the successful control is when we are able to achieve zero error in the complete functioning of the model. So let's continue building it. So we will take a sum block after this. So subsystem we will create after some time. So I'm not connecting it right now. I'm moving ahead. We have some blocks again like gain. So over here now, the output of this signal, after doing the PI control, we will be basically getting the vehicle tractive force. That will be the measured one. And then we will compare it with the vehicle resistive force and provide it to the sum block. So again, this will be the output as force. So we are going to convert it again into the mechanical signal. So we will use the component empty ratio here. The values of these constants will always be the same in the entire model. Again, we have another component here. So now after it is converted to the mechanical signal, we want to convert it into the electrical signal. So we are also using the EM ratio, or EM, I would say conversion, I can name it. After converting these signals, we will again have to feed it to the PI control. This time we are doing the PI control for the current part. So let's again search for a subsystem block, and we will just, for a reference right now, we are just placing it here like that. And after this, we will again take a sum block. After the sum, we are going to take a product block. The output of the sum, we will just connect to the first input of the product. At the bottom, we are going to connect the battery side voltage. And towards the end, we will just have to connect a limit block. And we will place a probe to observe the final output. So let's place a probe. Now, first of all, what we will do is we will create the subsystem part of the model. So let's get the PI control. So I will double click on the first subsystem which is there. Double click on subsystem 1. I will delete this part. And over here, I'm just going to take the reference signal. So I will take signal input port. Similarly, I will take another signal input port. So I will name the first one as measured. Then I will take a sum block and I will reverse the sign to plus minus in order to compare the reference with the measured. Let's connect them. Then we have the gain block. After this, we will take an integrator. And we will again connect a sum block over here. Connect the top part of the sum again. The bottom we will again connect to the measured. And the final output again going to the gain block. And finally, we are using it to go to the signal output port. Now we will just, change the names. So the gains have to be named as, this one is for the KI input and the second one is for the KP input. So the proportional and the integral coefficients, we have just named them. So for the first one, we have the value of KI calculated as 2.372. And for the second one, that is KP, we have the value as 6.5657 e to the power 3. So that's it. The PI control part is done. We can go back to the model now. So we have the vehicle control and the EMS unit. Now what we will do is just simply connect the reference to the top part. So reference we connect here. And the measured signal, we are simply going to connect it or at the bottom, that is on the vehicle velocity. After this, the final output will go to the top of the sum block. The bottom part now, we will just connect the bottom to the vehicle resistive force. So I will take another signal input port. The name I will change it to vehicle resistive force connected at the bottom of the sum block. Next, I will just delete the subsystem 2, and what I will do is I will simply copy and paste the subsystem 1 block here. So we don't have to create the same subsystem again, but pretty much the blocks will be same. Only the difference will be in the coefficient value of Kp and Ki. So I will just simply edit those values. Remaining part I have to keep it as same. At the measured input, we have the DC motor current. So again, I will take a signal input port and just place it here, change the name. This will be DC motor current. And I will just connect it here to the measured part. After this, we have again the sum block. So just the top part, we are going to connect it to the sum block. Next, we will take two more signal input port for the final signal input port. This one is the DC motor back EMF. So we will just place it and connect directly with the sum block. And lastly, we take the final signal input port. And this one is by the name of battery voltage. So just change the name, battery voltage, and I will connect it to the bottom of the product block. So that's it. Connections we have done so far. Now we have to first change the value of the Ki and Kp parameter inside subsystem 2. So let's double click and edit that. So the value of Ki in this case is calculated as 590.0282 and Kp we are going to put it as 2.1972. Again, we come back to the main model. Now we are left with some gain blocks and we have the limit block as well. Before, just populating those values, we are also going to change, we are also going to some gain and probes as well to observe different type of signals. So firstly, we will connect the probe at the very last signal, that is for the battery voltage. So let me just search for probe. We can connect it here. And again, I will just name it as battery voltage measured. Next, we will have a gain block. So let's search for gain. I will take another gain block here. So basically the back EMF that we are just doing the electrical conversion, and then we are providing it to another gain which is converting it into RPM. So we have it converted into the speed. So the EMF is being converted by using the EM conversion. This gain will be basically converting it to RPM. So I will name it as 2 RPM. And lastly, connect a probe again. I will again change the name of the probe. This time the name will be DC motor speed. Before this, now we will connect another probe here on the DCM current. So we will just name it as DC motor current measured, because all of these are the measured not from the drive cycle input that we will be providing. Then we will connect another probe at the output of the sum block and just name it as DCM voltage requested. Now at the top of the subsystem between the empty ratio and the M conversion, we are also going to take a gain block here. Again, use the same name, EM conversion. We will take a probe over here. It's connected between the two. The probe is going to be named as DCM requested current. And at the top, we have another probe connected directly to the signal. And we will change the name to DC motor torque requested. So this is it. Now we just have to provide all the input values. So if you remember, I had opened a presentation in which I had couple of signals where we had the drive cycle input output, and there was a graph which I had shown in the last slide. So for that graph we had the values of x and fx, which we are going to basically use as the input inside the drive cycle. So what we will do is we will just use the same value and provide it as an input here. So let me just open that sheet. Just give me a moment. I'll reshare my screen. Yeah, so I hope the screen is visible now. Can
Yes,
anyone?
ma'am.
Yeah, okay. So now you can see in this Word file I have opened, this is the input value for the x, and the bottom one is for the y, that is the function of x. So these are the data points which we use to plot that graph, which is speed versus time curve. And this is basically our input for the drive cycle. So what we are going to do is we are going to use the same points inside our model for the drive cycle input. So let me just share this in the chat also, so that whoever is creating the model and doing the hands-on along with me, or in future if you would like to do it, you can refer to these data points for input x and the y value. Now let me show you where we are going to use these inputs. So let's directly come back to the model. So first we have this clock block. So double click on clock and we will just delete the rate value and we will term it as a variable called TS. After this, we will take the drive cycle input. So again, double click. In the input value, we will just delete this part and we want to paste the part which is inside our sheet. So let's take the input x value. So you need to include the brackets as well. So just make sure that you are using all the values. Just in the same way, I will just paste it over there. Same thing I have to do for the fx part. We will use the y values here. And let's paste it here. After that, we will select the implementation as non-equidistant. We have the extrapolation method selected as linear, and execution rate we will leave it at inherit. Now these data points, they don't have actually the time synchronization with our model. That's why we have used a clock block before them, so that whenever these values are executed, they are executed at the same rate at which the rest of the model is running. So the model is running at a rate of ts. That's why we have used a clock to synchronize this graph to also run at the same execution rate. Next, we have used the kilometer per hour gain block. So we are just converting this drive cycle output, that is our speed, and the actual vehicle velocity into kilometer per hour range. So what we will do is just multiply by a factor of 3.6. Same thing at the bottom, 3.6. We have already, given the values for the KP and the KI system. So let's I would say mention the value of the other gain blocks. So at the top, you remember that we have used a percentage gain block. So this 2% gain, the value will be 100, because we are just simply converting the input value of the SOC into the percentage SOC. After that, we have the signal switch. In the signal switch, we will use the condition control is greater than and equal to threshold. And the threshold, we are going to keep it as 0.9. Next, we have the electric braking. In the electric braking, both the inputs, we are just going to keep a value of 0 and the execution rate as TS. I think I just mentioned 10. This is 0 and this one is also 0. So just denoting the braking through this part. Basically, whenever there will be some SOC, it definitely means that yes, the vehicle is moving and the battery energy is being utilized. So if the SOC is increasing, that denotes charging. If it is decreasing, that means the vehicle is moving and the battery power is getting consumed. So in that scenario, whenever we have the SOC, we will just read out what is the estimated SOC. And in case whenever there is no input coming from the SOC side, in that case, we will consider that the value is stationary, vehicle is stationary, there is no movement. So automatically the brakes have been applied and the brake force will be generated. Next, we have the subsystem for the empty ratio. So let's go towards the next block. The empty ratio value will be same, which we used in the mechanical transmission unit. This time we will just divide it. So it's 1 divided by 15.0654. We have the same value for the EM conversion, just in the factor. So we have 0.2865. And same for the above one. And there is another EM conversion here at the bottom. So this one also the same value, 1 divided by 0.2865. 2 RPM, which is placed here. So we will just keep the value as 30 divided by np dot pi. Now in Typhoon, because it is a complete Python based environment, so whenever we are using a variable which is associated in the Python library, we also have to use it in this syntax, like whatever is the function name dot whatever is the variable name. So inside the numpy function, we have the value of pi variable stored. So we are using it in this format, np dot pi. Okay, I think after this, the second subsystem also, we have just pretty much provided all the values. So what is remaining is just the limit block. So let's just put the final block limit. So the upper one, we will keep it as 1 because this is the modulation signal, and the lower one, we are keeping it as -1. And lastly, we have to finally declare what is the execution rate of this model. So at what time rate is the model completely going to run? So before that, let me come back to the model and we will just initialize it. Like I told in the first session, we have this model initialization script. So just open this script and we will just define the value of TS variable over here. So we have 1e minus 3. So at 1 millisecond, we are going to use this particular model. That's it. Let's click OK. Now, the only thing left is to connect all of these subsystems with each other. Once the connection is done, after that, we are having, only one work remaining, that is to construct the entire SCADA panel. So, of course, it will take some time, but let's start moving. So, for connection of the entire subsystem, let's just follow step by step. So there are some input output from every subsystem. Now we have the option to place those input output in such a way that the model looks clearer. So what I will do is because I already have a, I would say, image with me of the model. So using that image, I exactly know which signal is going to which block. That's why I'm just going to do the placement of those signal. This is not at all a compulsory step for anyone. So you don't need to actually follow this, but you should at least have an understanding how to do it. So suppose I start with lithium ion battery. I know that I require the battery SOC at the first output. So this one, I'm just going to double click on the battery SOC signal output port, and the side I will select as top, and the index number I have to select as at first. So what happens is, let me show you. When I go back, this is showing at the top, and right now no other signal is there, so this is showing at the center. But suppose if I select another signal at the top, then this will come at the first position. Similarly, I need one battery voltage also at the top, so I will select top and index number 2. I need one battery voltage on the right side, so I'll select right, index 1. And I think lastly we have the battery current, so this one is again on the right, index 2. Yeah. Next, we have the electric drive unit. So double click again. So we have battery voltage and battery current on the left index 1. And this one is again on left index 2. We have DC motor torque. This is going to the mechanical transmission. So this one will be on right at first index. And the speed is also going to the transmission unit. So again, right and at second place. Lastly, we have the mod ratio. This input is basically going to my controller. So I'll have it at the top with auto index, or I can just leave it like that. Okay, I can put 3. There are 2 other signals. So we have DC motor, I think back EMF and DC motor current. Yeah. So firstly, we will take the DC motor current. This is also at the top, index 1. And lastly, the back EMF. This is also at the top and at second place. Lastly, the third subsystem that we have is the mechanical transmission. So the brake force is coming from the controller part, so we'll keep it at top. The DC motor torque is basically coming from the left side at 1 position. This is also on the left. And wheel force and wheel velocity will be on the right, going to the next subsystem. Okay, next is vehicle dynamic. So I think, okay, just one more change. So we have wheel force on the left at index 1 and we have vehicle velocity. So one of the velocity is again on the left. Then we have vehicle resistive force. So vehicle resistive force is on the top at 1, and vehicle velocity will be again on top at 2nd. Now we have the vehicle control and EMS. So we will just shift, I think, battery SOC, battery voltage, DC motor current, and DC motor back EMF. These four are required at the left side itself. Okay, still let me do the numbering so it's very clear. So we have it on the left at 1. We have battery voltage at the left at 2. We have the DC motor current left at 3. And we have the DC motor back EMF again at the left and 4. Next we have the mod ratio. So the final probe, oh okay, we didn't name this one. So the final probe, which is the output of the limit block, let's just change the name to mod ratio. We will just, this is not a probe, this is actually a signal output port. I think by mistake I connected that. Let me just place a signal output port. Yeah. So this one is at the bottom and it connects to the drive unit. So let me just change the name mod ratio and we will select as bottom at index 1. Similarly, we have the brake force here. The brake force is again at the bottom at index 2. Lastly, we have the right side remaining. So we have vehicle velocity and vehicle resistive force. So vehicle velocity will be on the right side at index 1. And resistive force will be again on the right at index 2. That's it. Now let's get back. So this is pretty much done. Now let's connect all the subsystem blocks. So we just need to match the names. SOC with the SOC, voltage with the voltage signal, the DC motor current with the DC motor current signal, back EMF, we have the mod ratios, the brake force, we have vehicle velocity, and we have the resistive force. That's it. So this is the final, schematic editor model. Almost everything is complete. There is one additional thing in the model, like if suppose you want to insert any image inside this particular model, so any of the subsystem can also be initialized with an image. So if you would like to create your model in a better way, or you want to denote every subsystem with having its own display, so there is also option to do the import. So what we are going to do here, I will just show you how to import the image, the steps to import the image for one of the block. And you can just learn the procedure. We are not going to follow it for all the steps because we have limited time. So I want to complete this model for this session so that the next session, since I don't have the hardware access with me, my colleague, Mr. Shivam Shivastav, he will be taking the sessions for tomorrow, both the sessions. And he will be also showcasing you how to, basically use the Texas Instrument based microcontroller cards along with our real-time simulator and how to work with those example models. So I want that tomorrow session, because it's very interesting and very helpful. So it should be, aligned as per our discussion or as per our thought. So if we don't complete this model today, it will be an issue tomorrow. So that's why I would just like to complete this one. So I will show you the case for one, and the same process we have to follow for any of these subsystem. Let me just right click, and then we have this option of mask. So in mask, we have the option of mask editor. So click on mask editor. You can see this dialog box has opened. In this dialog box, we pretty much have some options here. We have handlers and we have requirement also. So inside this, we basically have the option of handler, in which we have the define icon option. So what we do is we just need to write the command over here. So what type of command we will use it? We will just initialize image, and in the bracket, we just need to mention the image where it is being stored. So what I will do is very quickly, I'll just go to the folder and just select the file. Let me show you which file I'm going to use. This is for the EMS part. Yeah, so this one. And I'm just going to cut and paste it in the HBTU folder where my model is saved. And I just need to know that what is the name of this file and what is the type of file. It is a PNG file or it is a JPEG file. So you can see this is a PNG file. The name of the file is driver and this is .png. So I have saved it in the same folder where my model is there. Now in double quotes, I just need to define what is the name and the extension driver.png. So that's it. Just click OK. So there is, I think, some issue. Let me see. Okay, I'll just do it one final time. It should work now. Okay, I think just a little issue I'm doing with the syntax. So yeah, we have provided the file extension, just only the name.png. I think that was the right one I was using, but it takes some time to load the image. So pretty much it's the same syntax which we used. It takes some time because it has to identify the path where the folder is saved, but the process is same. So similarly, we can do for all the 5 subsystems. So that's it. This is it in the model. Now let's again click on Control S and we will finally save the progress of the model till this part. And now we are ready to compile the model. So if there are any errors currently in the model, we will be seeing them now. So let's just quickly click on the compile button. So at the top menu bar, you can see the compile and load model in Hill SCADA with the red arrow. So just click on this icon. Okay, so we have one error: validation is not complete because electric drive product one input in is not connected. Okay, so I think I forgot to connect one of the product block here. This is connected to the mod ratio ref. Let's see if we have any other error or we might have forgot to connect something else. Okay, there are few errors. They have different execution rate. So let's see which one it is talking about: signal switch and the vehicle resistor force. So this is running at 100 micro and the signal switch is having a rate of inherit. So what we will do is we will just change the resistive force to TS as well, so that execution rate remains same for all the clocks. Now, same issue with the battery initial value and the max voltage. This one is T at inherit. Let me also change this to TS. Yep. So for all of these, we need to have the same execution rate. So we didn't change those values. That's why we are having this issue. Let me change it for all the constants. So because we need the entire model to be running at the same rate. Okay, so no other error. So our model is finally validating, and let's wait for it to compile completely. It's a complete signal processing based model, so compilation will not take a lot of time. And you can see model got compiled successfully. And as soon as it got compiled, we have a new window open in front of us, which is the Hill SCADA window. In the Hill SCADA now, we directly have a dialog box popping up, which is asking whether to load the model in the virtual environment. So just like we did in the previous model, because we are not connected to any hardware, we can simply run the model in the virtual environment also. So just click on load model to virtual Hill. Let's wait for all the settings to load, and after that we will start building the SCADA panel. Okay. Now what we will do is, again, for this model, we have to create a new SCADA panel. So we will just click on this plus button, create new panel. On the left side, we have a widget library. So we are going to create a panel by using different type of widgets here. So very first of all, we will just initialize few of the settings. So just like we had an initialization script in the schematic editor, we have another one over here. This is also Python supported. So we will just define the, variables here. So we will use a variable by the name of storage underscore inverter underscore status. So even though this is a model which is basically based on signal processing components, but we are still trying to replicate it in the exactly same way how a normal vehicle is created by using the plant components. So for example, if there is an inverter, we usually enable or disable it. So we are just providing this status here that the storage inverter is turned on. So the status has been denoted as on. We are also having the nominal current. So I nominal is equal to the 300, and we will also just write a comment here that for this converter rating. Similarly, the operation mode that we are having, so we will write as charge, and just a comment here also that this is a global variable valid for the entire model. And lastly, we have an I reference, which we are going to keep as 1. So just 4 lines of small code we have here, where we are defining couple of, initial values. Okay. Yeah, that's it. So let's click OK, close it. And now we will start with the model. Now we have to do one thing is, at the base of the model, we will take an image over here also. So it's possible to take images inside the SCADA panel also. Let me just quickly copy the image in this folder that I want to use. Okay, the vehicle chassis. And I'm just going to paste it over here. So now what I will do is, from the left side library of the widgets, if I scroll down, you can see there is one heading called visual. Inside visual, you can see the image option is there. So directly drag and drop this image block, double click here, and we can have this, import option selected here. So we will just click on select image, go to the same folder, and we will use this vehicle chassis image. After this, you will see that the new image is imported here. Now we want to use this as the background for my model. Above or top on this, we are just going to place different subsystems and subpanels. So I'm just going to fix it on the screen. So I need a big size, model here. Let me just expand it so I can place it in the entire screen. Yeah, I think this is fine. Again, I will double click and I will just check on this box called as set as canvas background. So once I check it, it is going to lock in this position. So now even if I do something on top of it, this particular image is not going to move from its place. So that's why we are just using that option to lock it in this position. Now we are going to take couple of other widgets. So as we had 5 subsystem blocks in the schematic editor, similarly we have 4 of the sub panels inside the SCADA panel. So again, from the visual itself, we have the option of using sub panel. So let's just drag and drop and place 4 of the sub panel as required in the model. So I will just place them according to the position. So first one goes here between the red and the green arrow. The second one goes between the 2 green arrows. The third one, we are going to put it at the bottom between the red and the green arrow. And the last one, again, between the green arrow and the silver bar. Now, other than these 4 sub panels, we are also going to take 4 gauge. So gauge is under the monitoring widget because it is able to show us what type of output we are getting. So inside the monitoring heading, you will be able to find the gauge. So let's just search for it and then place it. So the first one, we'll keep it between these 2 sub panels. Just like that. Let me see if I can change the size even more. Yeah, this is fine. Next, we will take one at the bottom here. After this, we will take the next one in between these 2 subpanels. And last one we will take at the top above this panel. That's it. So 4 of the gauge components and 4 subpanels. Now let's quickly name each of them. So we will start with the first subpanel from the left. So this one, okay, not double click, just right click, go to properties, and just change the name to battery storage. I will complete it very quickly so that we finish on time. I'm hoping to complete the model. Then we have the second one. This one is named as propulsion. We have the third one again in properties. So this one is mechanical transmission. And lastly, we have the fourth one by the name of control center. Okay. Next, we have the gauges. So we will just name them one by one. So at the bottom, we have the DC motor speed. So we'll just name it DCM speed. In the bracket, RPM. The second gauge we have, this one is for the DC motor torque. In the bracket, Newton meter. Here we have the vehicle velocity. In the bracket, we have kmph. And the last one we have again at the top, that is battery SOC. So what we will do is for all the 4 gauge that we have named, we just need to assign the signal that we want to visualize in this panel. So we will just double click, and at the bottom you can see there is this option of analog signal. So I will just name all the 4 signals that we are going to select here. In the battery, sorry, this one is I think DCM speed. So we will just search for DCM speed. So you can see we are able to find the name of that particular signal in this list. So similarly for all the 4 we have to do. Suppose for battery SOC, I will just search battery SOC estimated. So you can select this one. Okay. Sorry. Yeah. So we just added battery SOC here. Let me find it again. Battery SOC estimated. This one is for the DCM speed. Next, we have the DC motor torque. So you can just search for DC motor torque, and we will take the one with the DC motor torque requested. And last one, we have the vehicle velocity. Here we will just search for vehicle velocity or vehicle speed. Okay. Now the most important panel amongst all 4 is the control center, because here only we are going to observe all the result. So what I'm going to do is I will take a few widgets inside other 3 panels to quickly show what all values we are getting, but we will focus on the control center one. So let me just quickly take 3 digital display. Yeah, so you can see similarly we have another one. So 3 of them. And there are 3 things that we want to see inside the battery pack. One is the SOC, one is the voltage, and one is the current. So similarly, quickly, we will just name them. This one is SOC. You can use SOC estimated signal. After this, we have voltage and current. Now to display these, you can also use other widgets for monitoring, like trace graph is there. So you can use trace graph also. You can also go for gauge widget. So multiple widgets are there. So that is completely optional. Because we just want to see what value we have, I'm just taking digital display. It's completely optional for you to take any. So you can see we have battery voltage measured. And the last one we have is the battery current. So let me just search for current. Okay, I think it's okay. Let me see the name. I think I used a signal. Okay, I think I haven't placed a probe at the battery current. Let me quickly do that. Okay, so the name is probe 1. I actually didn't change the name of it. So what I will do is, instead of searching for battery current, I will search for probe 1. Yeah, you can see. Just select this, come back. Now we have the propulsion subsystem. So inside propulsion, what is most important to visualize? It is the torque and the speed, and along with that, whatever is the DC motor voltage and the current. So we will take 2 gauge. Okay. And at the bottom, we will again take 2 digital display. Or what I will do is I will go for trace graphs here. Let me take 2 trace graph. So in the first one, we will just name it as speed, and we'll search over here for the DC motor speed. Next one, we have the torque, and we will just search for DC motor torque requested. Then in the graph, because this is for the DC motor voltage and current, so we will just try DC motor voltage We will add one of the analog signal and again do the same process. DC motor, voltage requested. And over here we have DC motor current. So again, add one of the signal and we will search for DC motor. Done. Let's come back. Third is the mechanical transmission. In the mechanical transmission, we know that we only have the force and the velocity. So we will just take two of the digital display here, or we can take gauge also. So let's take two gauge and just name them. One will be the vehicle velocity. Let's search for the signal name. So this is by the name of vehicle speed. And the second one we have, it is traction force. And you can just search for it. So the name for the traction force will be vehicle tractive force. That's it. So we are done with the mechanical transmission. Now let's come to the control center. So this is the final, sub panel. So we will create the entire panel here. What we are first going to do is we have to divide it into three parts. So we will take a group here. So let's take three of the group and drag and drop them. The first group at the top. This is also inside the visual heading. One group. Similarly, we will take another one at the bottom. And similarly, we will take another one. Let's rename them. So the top one, this is vehicle measurement. The second one is traction machine. And we have the battery storage. So similar signals we are going to see at one place here because this is the control unit just to validate that everything is working properly. So again, inside it, we will take some widgets for monitoring. So very first of all, we will take gauge at the top here. We will take two more gauge. One will be here and another one over here. Then we will take, I think, trace graphs. So we have one trace graph over here. We have another one over here. We will take one over here. And we need one, or I think we can skip that because it's for the same signal. So we have gauge as well as graph both for the SOC. So it's better if we take only one. Similarly, we will just resize them. That's it. And let's see if we can take one more here. Okay, I want to reduce the size of this one. And in the same way, I want to take another graph here. I have to, I think, expand this particular panel. Let me see. Yeah, because this signal is the mod signal. So it's important to show. That's why I'm just doing this. Anyways, you can set it in a better way later on also when you are doing the hands-on. I'm just, for showcasing the signal, I'm doing this part. Yeah. This is fine, I think. Okay. Now let's start naming them. So the very first one is vehicle velocity. Here we have the update rate as 250, analog signal, the decimal is 2, and then we will search for the vehicle speed. After this, we have scaling as same. We will go to the advanced settings. Here we have minimum as 0, and in the maximum, we will select 60. Then we have the trace graph for the requested velocity. So we will just name it as vehicle requested velocity. We will add a signal here and just search the same vehicle requested. Sorry, we'll search for requested speed. And over here, we are going to see the measured speed as well. So now this is the most important graph because the requested and the measured, they should match with each other. Then only we can validate that yes, the drive cycle is actually following the input. So let's quickly name it as vehicle measured velocity. Add the signal here. We'll name it as, just a second, vehicle speed. At the bottom here, we will just take battery SOC. Just search for SOC here. And this one is 250. Click OK. Here we have the speed. The update rate will be 250. We are just searching for the DCM speed. And in the advanced settings, we will set the range between 0 to 2000. And the other two trace graph which are left at the end, this is the speed graph. So we'll just quickly add it. So by the name of DCM speed only. Click OK. And the bottom one, we are just going to name it as the mod ratio. Or sorry, it's the torque. And we will add the signal here by the name of DC motor torque. That's it. Just a second, let me just check one more thing and then we are finished with this. So we will just quickly run the model and see what kind of result we are getting. So just one little change in the advanced settings. We need to change the time window to 200 seconds for both the results. Done. So finally, we have completed this panel as well. And along with this, we have completed the SCADA panel. You can just go to file, okay, not file. Here we have these red arrows, which are helpful to save the panel file. So you can just save this panel if you have created now, and we are ready to run the model. So let's click on the green play button and let's start the model. So you can see what is the initial battery SOC we have. This is around 90%. Now what is happening is we are just following the same graph. So in the graph that we have seen, we just had one, the constant line at the beginning. After that, slowly we started accelerating. So once we accelerate slowly, you will see that, okay, the DC motor speed will start increasing, the torque will increase. Similarly, the velocity will rise. And because vehicle is moving, the SOC will be consumed. So you can see the same behavior here. After that, it will remain constant for a few seconds. Once it is constant, then it will start deaccelerating and the torque will move towards negative and similarly the speed also. Next, what we have, again, it will go back to 0 and remain constant. So everything later on will again become 0. Once it is 0, it's dropping to 0. After that, again, it will start to accelerate. So you can see how the torque is again positive. So let's see what kind of, figures or values we are getting here. We have SOC, battery voltage, and we have the battery current here. We have the propulsion system, so we have the control. Sorry, this is the DC motor voltage and DC motor current, as well as the speed and torque values. We have the mechanical transmission unit with the vehicle velocity and the traction force, and we have the control center. Okay, so I think there is some issue here because it's not ideally exactly matching the behavior. However, now you can see again it started accelerating, so the behavior is changing. But this is in reverse way. So I think something in the model is missing. Let me see if I can quickly change it. Okay. I think there is just a little bit change of execution rate somewhere. So in all the blocks, we did not mention the execution rate as TS, because of which the time synchronization is not proper. But of course, it will take some time for us to, do the changes again. Instead of that, because we are already above time, so I will stop the session here, but I'm going to tell you for reference where this example is actually saved. So once you open the software, the very first window which you open, you can see the example section. In example section, you can just search for EV, and once you type EV, you will get okay, SP. Yeah. So this is by the name of electric vehicle SP. Inside electric vehicle SP model, you will find the same example. It is already present in the example section. You can open this model, you can check what is different in our model and this model, and accordingly make changes, edit your own file, and you are ready to have the model. So reference also I have told, in case like any of you is facing any issue, you can try to modify it. However, it's a very small change that will be there. I'm pretty confident because I've made it in hurry. So I think because of that, somewhere we have missed out the execution rate part. But I hope that everyone understood the model, and that's it from my side. So if there are any questions, you can drop it in the chat. If not, I have informed my colleague that he will be addressing to the question initially in tomorrow's session also. So in the morning also, when the first session starts, if you all have any questions related to this example, he can also answer them. So as of now, I think it's over time, so I'll stop here. So thank you once again, everyone. Over to you, sir.
Thank you, Ira. Soumya, are you available? Soumya?
Yes, sir, I'm available. Yes, sir, I'm available.
Are you going to do vote of thanks or I should do? Okay, thank you, Ira. Thank you once again for such a wonderful session. It was really very, very nice, and I hope that all participants get benefited by this open Typhoon Hill simulator toolbox, and in future they will also have hardware related to this. And tomorrow we have session of Shivam. He is also from Opel RT. So the complete package related to Opel RT is, I am sorry, Typhoon Hill, because see, Ira, I am very sorry for that. Actually, I itself I took talk related to Opel RT. That is why that was the slip of tongue. And I hope tomorrow session all the participants join the session and get benefited by the person from the Opel RT. So thank you very much. Good night.
Thank you, everyone.